Every detail in this story comes from real scientific research and observation. There is a rock in space. It is not large by cosmic standards, roughly 500 meters across, approximately the height of the Empire State Building if stood on its end. It tumbles slowly through the inner solar system, completing one full rotation every 4.3 hours, tracing an oval path that brings it close to Earth once every 6 years. It has been doing this for billions of years. Nobody knew it existed until 1999. And when scientists finally calculated where it was going, not just next year or next century, but in the year 2182, the number they arrived at was not zero. A rock born in the earliest moments of the solar system, carrying inside it carbon molecules and water-bearing minerals that predate the Earth, has a measurable probability of returning to the body whose chemistry it may have helped create. That probability, as of the most recent calculations, stands at roughly 1 in 2,700. Before the spacecraft launched, mission scientists built models of Bennu's surface. The models predicted fine gravel, loose dust, open terrain wide enough to land on safely. When OSIRIS-REx arrived after a 2-year journey and turned its cameras toward the surface, the images that came back did not match the models. Bennu was covered in boulders. Thousands of them, some a meter across, some 5. Some towering 12 meters above the surrounding surface on an asteroid barely 500 meters wide. There was almost no flat ground anywhere. The entire landing strategy had to be redesigned. In deep space, with a communication delay of 18 minutes each way, while the spacecraft orbited a body so gravitationally weak that a person standing on its surface could leap to escape velocity with a single strong jump. Then, in early 2019, something else appeared in the data. Bennu was throwing rocks into space. Particles were launching off the surface, not once, not in a single unusual event, but repeatedly from multiple locations, captured in image after image by cameras that had been designed to map terrain, not watch a living surface eject its own material into orbit. Nobody had seen this at an asteroid before. Bennu was not a passive rock, it was doing something. The spacecraft sent to answer these questions was named OSIRIS-REx. It traveled 2 billion kilometers. It orbited Bennu for nearly 2 years. On October 20th, 2020, it descended to the surface and made contact for exactly 5 seconds. When it lifted away, images showed the spacecraft had sunk 48 centimeters into material so loose it behaved more like water than solid ground. The sample capsule it brought home, landing in the Utah desert on September 24th, 2023, contained approximately 250 grams of material from a body that formed before the Earth existed. Inside that material, carbon, clay minerals that could only have formed in the presence of liquid water, organic compounds that are the chemical precursors to amino acids. The building blocks of life carried through the solar system for 4.5 billion years inside a rock the size of a skyscraper on a trajectory that brings it back toward Earth every 6 years. This is the story of Bennu. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. In the late 1990s, A search program called LINEAR, the Lincoln Near-Earth Asteroid Research Program, was conducting one of the most systematic sky surveys ever attempted. Operated from a field site in Socorro, New Mexico, a collaboration between MIT's Lincoln Laboratory and the United States Air Force, it used a pair of 1-meter telescopes to image large portions of the sky on a nightly basis, processing the data with automated detection software designed to flag anything that moved against the fixed background of stars. The logic behind such surveys is simple in concept and demanding in practice. Stars are effectively stationary on the timescale of human observation. Planets move slowly and in predictable arcs. But asteroids, small rocky or metallic bodies orbiting the Sun, move at angular velocities that can be measured from one night to the next, and sometimes within a single observing session. By comparing images taken of the same sky region, hours or days apart, detection software can identify the signature of an object moving through the field of view. On September 11, 1999, LINEAR's system flagged an object. It received the provisional designation 1999 RQ-36. The label encodes the year of discovery and the order of discovery within a particular 2-week window. It was a standard format asteroid designation, unremarkable in appearance among the thousands of similar designations generated annually by surveys of this kind. What made 1999 RQ-36 immediately notable was its orbit. The object's calculated trajectory placed it on a path that periodically crossed the orbital path of Earth. This put it into the category formally defined as a potentially hazardous asteroid, a classification applied to any near-Earth object larger than 140 meters across, whose orbit brings it within 0.05 astronomical units of Earth's orbit. 1 astronomical unit is the average distance from the Earth to the Sun, approximately 150 million kilometers. 0.05 astronomical units is about 7.5 million kilometers. 1999 RQ-36 met both the size and proximity criteria. The LINEAR program itself was a turning point in humanity's awareness of the small body population of the solar system. Before systematic surveys of this type, the known population of near-Earth objects was sparse, a few hundred bodies cataloged through decades of observations, mostly by individual astronomers following up on chance discoveries. LINEAR changed the scale of discovery fundamentally. Using automated detection software and a dedicated observing strategy, the program identified more than 230,000 asteroids during its operational period, including more than 2,000 near-Earth objects. The rate of asteroid discovery during the late 1990s and early 2000s increased so dramatically that the total known near-Earth object population grew from under 1,000 to tens of thousands within a decade. 1999 RQ-36 was one discovery among many, but its combination of orbital characteristics, physical size, and composition made it stand out. Radar measurements from the Arecibo Observatory in Puerto Rico, home to what was then the largest single-aperture radio telescope on Earth, a 305-meter dish constructed in a natural karst depression, and from the Goldstone Solar System radar in California, began resolving the asteroid's shape and physical properties, with a level of detail unavailable through optical imaging alone. Radar ranging works by sending a precise radio signal toward an object and timing the return. By analyzing the Doppler shift of the reflected signal, the way the frequency changes based on the relative velocity of the reflective surface, the rotation rate, shape, and surface texture of a distant body can be derived. The radar returns from 1999 RQ-36 were revealing. The object was roughly spheroidal, with a pronounced equatorial bulge, a distinctive spinning top shape. This shape is not coincidental. It is the product of rotational dynamics acting over geological time. As a body rotates, centrifugal acceleration directed outward from the rotation axis acts on surface material. Over millions of years, material migrates toward the equator, building up the characteristic ridge. Its mean diameter was measured at approximately 490 meters, with a maximum equatorial diameter of about 565 meters. Its mass was estimated at 73 billion kilograms. Its surface was unusually dark, reflecting only about 4% of incoming sunlight, similar in albedo to fresh asphalt. This low albedo is the characteristic signature of carbonaceous material, placing the asteroid in the B-type taxonomic classification, a subtype of the broader carbonaceous class, thought to preserve some of the most primitive, least thermally processed material in the solar system. Primitive, in this context, means something specific. It means material that formed in the earliest period of solar system history and has not been significantly altered since. B-type asteroids are rare. They are thought to be related to some classes of carbonaceous chondrite meteorites, including the Tagish Lake meteorite that fell over British Columbia in January 2000, whose fragments were found to contain amino acids, polycyclic aromatic hydrocarbons, and even presolar grains that formed inside an ancient star before the sun existed. In 2013-1999, RQ-36 received a permanent name through a competition open to students 18 and under. The winning suggestion came from a 9-year-old student in North Carolina named Michael Puzio. He proposed Bennu, the name of an ancient Egyptian deity associated with the heron bird, with creation, and with the sun. In Egyptian mythology, the Bennu was said to have been the first living creature, rising from the primordial waters at the moment of creation, its cry breaking the original silence of the universe. The name was accepted by the International Astronomical Union. Bennu. The coincidence of that name, a primordial bird associated with creation and the origin of life, given to an asteroid that may have helped deliver life's chemical ingredients to the early Earth, was not lost on the scientific community. Bennu orbits the Sun with a period of approximately 436 days, about 1.2 Earth years. Its orbit is inclined about 6 degrees relative to Earth's orbital plane, and its eccentricity is approximately 0.20, meaning it follows an oval path that carries it from 0.897 astronomical units at closest approach to the Sun to 1.356 astronomical units at its farthest. This places it in a class of near-Earth asteroids called the Apollo group, whose orbital paths cross within Earth's orbit. Every 6 years, Earth and Bennu approach each other relatively closely. What scientists calculated from the precise measurements of those approaches was troubling. Using the mathematical framework of orbital mechanics, accounting for the gravitational influence of all 8 planets, the Moon, and even major asteroids, researchers ran forward projections of Bennu's trajectory across multiple centuries. The projections identified a cluster of potential impact opportunities concentrated between 2169 and 2199. The most significant date is September 24th, 2182. The probability of impact on that date is currently estimated at approximately 0.037%, one chance in 2,700. For an object the size of Bennu, an impact would release energy equivalent to approximately 1,400 megatons of TNT. The Tsar Bomba, tested by the Soviet Union in 1961, yielded approximately 50 megatons. A Bennu impact would be equivalent to nearly 28 of those devices detonated simultaneously. The affected area would span hundreds of kilometers. This probability is not zero, and it is strongly dependent on something called the Yarkovsky effect. When sunlight strikes the surface of a rotating asteroid, the surface absorbs solar radiation and heats up. As the surface rotates away from the sun and into shadow, it gradually radiates that stored energy away as thermal infrared radiation. Because the asteroid rotates, the hottest part of the surface is slightly displaced into the afternoon, the region that has been in sunlight for some time and has accumulated heat. This asymmetric radiation creates a tiny but real thrust. Over 1 year, this effect is negligible. Over 100 years, it shifts an asteroid's orbit by tens of kilometers. Over the timescale relevant to Bennu's potential 2182 encounter, a century and a half, the accumulated drift determines whether Bennu threads a gravitational keyhole during its 2135 Earth flyby. A keyhole is a specific region in space, typically a few kilometers to tens of kilometers across, that, if an asteroid passes through it during a close approach, gravitationally deflects the asteroid onto a trajectory that results in a later impact. Current models predict that in September 2135, Bennu will pass Earth at a distance of approximately 185,000 to 310,000 kilometers, closer than the Moon's average distance of 384,400 kilometers. Whether Bennu threads one of the impact-leading keyholes in that 2135 encounter depends on exactly where it is in its orbit at that moment. And where it is depends on the cumulative Yarkovsky drift between now and then. The Yarkovsky measurement for Bennu, first made in 2013 using radar data from Arecibo and Goldstone, placed the annual orbital drift at approximately 284 meters per year. That number, refined by the OSIRIS-REx mission, is now directly embedded in every probability calculation concerning the year 2182. This is why Bennu was chosen as a mission target. Not just because of its scientific richness, not just because of its pristine chemistry, but because understanding it precisely, measuring it, touching it, bringing a piece of it home, is directly connected to understanding what it will do in 157 years. The mission designed to answer these questions was named OSIRIS-REx. The acronym stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. The name was also a deliberate echo of Egyptian mythology, Osiris, the god of death, resurrection, and cycles, paired with Bennu, the primordial bird of creation. Two names from the same ancient cosmology. A mission to touch the beginning of time, funded in part by the possibility of a future end. OSIRIS-REx was proposed to NASA's New Frontiers program, a category of medium-class planetary science missions in the early 2000s. It was selected for development in May 2011. The principal investigator was Dante Loretta, a professor at the University of Arizona's Lunar and Planetary Laboratory. The spacecraft was designed and built by Lockheed Martin Space in Littleton, Colorado. On September 8, 2016, OSIRIS-REx lifted off from Cape Canaveral on an Atlas V 411 rocket and began its journey. The spacecraft that would travel to Bennu was designed with a single non-negotiable requirement at its core: return a sample of Bennu's surface material to Earth without contamination. Everything else in the mission architecture served that goal. OSIRIS-REx's scientific payload was comprehensive. OCAMS, the OSIRIS-REx's camera suite, consisted of 3 cameras at different focal lengths. Polycam was a long-range telescope capable of resolving features as small as a centimeter from several kilometers. MapCam was a medium-field imager with 4 color filters used for global mapping and color characterization of the surface. SAMCAM was positioned to directly observe the sample collection process itself, the one event the entire mission had been built around. OLA, the OSIRIS-REx laser altimeter, contributed by the Canadian Space Agency, used laser pulses to build 3-dimensional topographic models of the surface with centimeter-level accuracy. It measured distance by timing the return of each laser pulse and could build detailed point cloud maps of terrain that no ground-based system could approach. OVIRS, the visible and infrared spectrometer, measured reflected and emitted light across wavelengths from 0.4 to 4.3 micrometers, a range that includes the spectral signatures of minerals, organic compounds, and water-bearing materials. OTS, the thermal emission spectrometer, measured emitted thermal infrared radiation to characterize mineralogy and map surface temperatures through Bennu's full rotation cycle. REXIS, the regolith X-ray imaging spectrometer, built by MIT students, measured X-ray fluorescence induced by solar X-ray flux. By analyzing the characteristic X-ray energies emitted by different elements, it could map the elemental composition of the surface. And at the center of everything, TAGSAM, the touch-and-go sample acquisition mechanism, was the physical instrument that had to actually collect the material and return it home. It consisted of a round contact pad approximately 30 centimeters in diameter, mounted on the end of a 3.35-meter articulated arm. The pad contained openings connected to a collection canister and a supply of compressed nitrogen gas. On contact with the surface, the nitrogen would fire, stirring surface material into suspension, and the suspended particles would be captured by filters inside the collection container. The design allowed for up to 3 sample collection attempts, using 3 separate nitrogen charges. Each contact was planned to last approximately 5 seconds. The minimum sample mass required to declare the mission successful was 60 grams, roughly 2 ounces of material from a body 300 million kilometers away. The spacecraft's total launch mass was 2,110 kilograms, including 1,230 kilograms of propellant. Its solar panel span at deployment was 6.2 meters. It was, by the standards of deep space exploration, a relatively compact spacecraft built to a cost cap within the New Frontiers program budget, but it was engineered to survive a 2-year journey outward, spend nearly 2 years in orbit around one of the smallest bodies ever orbited by a spacecraft, make physical contact with a 5 billion-year-old surface in a brief surface contact, and return its contents intact to the Utah desert. The Atlas V 411 rocket that carried OSIRIS-REx off the launch pad on September 8, 2016, generated approximately 3.8 meganewtons of thrust at sea level. The spacecraft separated from the upper stage 55 minutes after liftoff, deployed its solar panels, and established contact with the Deep Space Network. Everything it had been built to do was still years away, but the journey had begun. One aspect of Bennu's orbital dynamics deserves deeper attention before OSIRIS-REx's story continues: the architecture of the 2135 close approach and what it means for the century that follows. The concept of a gravitational keyhole was first developed in detail by planetary scientist Owen Botke and colleagues in the context of near-Earth asteroid hazard assessment. In simple terms, a keyhole is a small region in space, defined relative to a planet's gravitational sphere of influence, that, if an asteroid passes through during a close approach, results in a resonant orbit that leads to a specific future impact. The mathematics of keyholes emerge directly from the n-body problem, the challenge of predicting the motion of multiple objects under mutual gravitational influence. When an asteroid makes a close approach to a planet, the planet's gravity deflects the asteroid's orbit. The angle and magnitude of that deflection depend on how close the asteroid passes and at what velocity. For most trajectories through the close approach region, the deflection sends the asteroid onto an orbit that avoids Earth in all subsequent centuries. But for a narrow set of trajectories, the keyholes, the deflection angle is precisely such that the asteroid ends up in a resonant orbit, a path whose period is a simple integer ratio of Earth's period. In a resonant orbit, the asteroid returns to the same region of space relative to Earth after a fixed number of orbits. If that region of space is near Earth's orbit at the right time, an impact becomes possible. For Bennu's 2135 approach, the relevant keyholes are regions approximately 100 to 800 meters across. In the close approach geometry, whether Bennu threads one of those keyholes depends on where exactly it crosses Earth's orbital plane during the 2135 encounter, which depends on the accumulated Yarkovsky drift between now and then. The OSIRIS-REx mission measured the Yarkovsky drift parameter for Bennu to an accuracy previously impossible from ground-based observations. The updated measurement, incorporating 2 years of precise spacecraft tracking data, reduced the uncertainty in Bennu's 2135 position by a factor of approximately 8 compared to pre-mission estimates. The updated impact probability for 2182, 0.037%, or 1 in 2,700, represents the most reliable estimate available as of the mission's results publication in 2023. That number may change further as analysis continues and as ongoing radar observations add additional astrometric data points. The question of whether Bennu will strike Earth is not permanently settled by OSIRIS-REx, but the mission moved the answer from uncertain to considerably less uncertain. It gave planetary defense scientists the most precise picture they have ever had of a potentially hazardous asteroid's long-term trajectory, and it did so by going there. The trajectory OSIRIS-REx followed after launch was not a direct path to Bennu. Deep space missions rarely fly in straight lines. The energy required to simply aim a spacecraft at a distant target and burn continuously until arrival is prohibitive. The propellant mass would dwarf the spacecraft itself. Instead, mission designers use the gravitational architecture of the solar system as infrastructure, routing spacecraft through planetary flybys that provide velocity changes for free. OSIRIS-REx spent approximately a year in solar orbit after launch, looping around the Sun on a trajectory carefully calculated to return it to Earth's vicinity at exactly the right moment. On September 22, 2017, the spacecraft flew past Earth at an altitude of 17,700 kilometers, passing over Antarctica. The flyby added 3.78 kilometers per second to the spacecraft's heliocentric velocity, a change that would have required burning an enormous quantity of onboard propellant to achieve otherwise. That single gravitational interaction with Earth bent the spacecraft's trajectory outward toward Bennu's orbital radius. The navigation team at NASA's Jet Propulsion Laboratory tracked OSIRIS-REx continuously through the Deep Space Network, a system of large antenna complexes spaced 120 degrees apart in longitude around the Earth, located in Goldstone, California, Madrid, Spain, and Canberra, Australia. This spacing ensures that as Earth rotates, at least one complex is always oriented toward any given spacecraft in the inner or outer solar system. The Deep Space Network is one of humanity's most important and least celebrated technological assets, built over 6 decades, beginning with tracking needs of the first interplanetary missions in the early 1960s. Its largest antennas span 70 meters in diameter. They were originally built for the Voyager encounters with the outer planets and remain operational today, still receiving the faint signals from those spacecraft at the edge of the solar system while simultaneously communicating with dozens of active missions. For OSIRIS-REx, the distance to Bennu during the mission varied from approximately 1.2 to 2.3 astronomical units, depending on orbital geometry, corresponding to signal travel times of roughly 10 to 18 minutes one way. This delay defines how deep space operations actually work. When mission controllers send a command to OSIRIS-REx, it takes up to 18 minutes to arrive. When the spacecraft executes the command and the resulting telemetry begins streaming back, it takes another 18 minutes for that data to arrive at Earth. The round-trip delay for any action-reaction loop is up to 36 minutes. Real-time control of a spacecraft at Bennu's distance is therefore impossible. Every maneuver, every engine burn, every camera acquisition, every instrument measurement was decided days or weeks in advance, translated into command sequences, uplinked to the spacecraft, and executed autonomously according to a pre-programmed schedule. The spacecraft had to handle anomalies and unexpected conditions without human intervention, relying on onboard fault protection software to make autonomous decisions within defined parameters. This is one of the defining realities of deep space exploration, a machine built by human hands, operating on instructions uploaded days earlier, making decisions in real time that humans will learn about nearly half an hour after the fact. The control rooms on Earth are, in a meaningful sense, observers. The spacecraft is on its own. By August 2018, OSIRIS-REx was close enough to Bennu that Polycam, the mission's long-range telescope camera, could begin resolving it as something more than a point of light. The earliest images confirmed the expected spinning top silhouette derived from radar observations. The equatorial bulge was visible. But as the distance decreased and resolution improved, the surface began to resolve in detail. And the detail did not match the predictions. The mission planning had been built around a surface covered in accessible regolith, the loose, fragmented surface layer of fine particles that accumulates over geological time through micrometeorite bombardment and thermal cycling. On the Moon, Regolith is meters deep in most places. On Itokawa, the small asteroid studied up close by Japan's Hayabusa mission in 2005, regolith had collected in pockets between larger boulders. The models predicted Bennu would have similar terrain. What Polycam showed was a surface buried in rocks. Thousands of boulders distributed across the entire surface, some a meter across, some 5. Some near the South Pole, reaching 12 meters in height, taller than a 2-story building on an asteroid barely 500 meters wide. Open terrain was almost entirely absent. The science team stared at the images. OSIRIS-REx entered orbit around Bennu on December 31st, 2018, setting a record as the first spacecraft to orbit such a small body. The gravitational environment it was operating in was extraordinary. Bennu's surface gravitational acceleration is approximately 6 microgauls, 6 millionths of standard Earth gravity. At the orbital altitudes OSIRIS-REx was maintaining, around 1 to 2 kilometers above the surface, the Sun's gravitational pull on the spacecraft was stronger than Bennu's own gravity. Maintaining a stable orbit required continuous navigation calculations and periodic small engine burns. The orbital campaign that began in January 2019 transformed OSIRIS-REx from a traveling spacecraft into a scientific observatory, systematically mapping every feature of Bennu's surface. OLA, the OSIRIS-REx laser altimeter, built by the Canadian Space Agency, used laser pulses to build 3-dimensional topographic models, accurate to within a few centimeters across the entire surface. Polycam imaged terrain at sub-centimeter resolution from low orbital altitudes. OVRs, the visible and infrared spectrometer, analyzed the spectral signatures of minerals and compounds across the surface. One measurement derived from this orbital campaign was particularly important. Bennu's bulk density, calculated by measuring the tiny gravitational perturbations the asteroid exerted on the spacecraft during controlled close passes, came out at approximately 1,190 kilograms per cubic meter. Water has a density of 1,000 kilograms per cubic meter. The individual rocks on Bennu's surface, analyzed spectrally and compared to laboratory analogs, have densities closer to 2,500 kilograms per cubic meter. The discrepancy between the bulk density of the whole body and the material density of its individual rocks has one explanation: empty space. Bennu is about 40% empty space by volume. It is not a monolithic rock, it is a rubble pile, an aggregate of individual rocks and boulders, loosely bound together by gravity, so weak that the cohesive force holding the entire structure together is barely measurable. If a person standing on Bennu's surface pushed against a boulder with moderate force, they might send it into orbit. If they jumped with anything beyond a gentle step, they could achieve escape velocity. The escape velocity from Bennu's surface is approximately 20 centimeters per second, slower than a leisurely stroll. The asteroid's gravity is strong enough to hold rocks together over geological time, but barely. This rubble pile structure is believed to be the result of a catastrophic collision event somewhere between 700 million and 2 billion years ago, in which a larger carbonaceous parent body, perhaps 20 times the size of Bennu, was shattered by an impact. The fragments from that collision slowly gravitationally reaccumulated under their mutual attraction, assembling into the body now designated Bennu. Crucially, the energy of the original collision was sufficient to shatter but not sufficient to melt. The material in the fragments was not significantly heated by the impact. Its chemistry was preserved. This is what makes Bennu's composition so scientifically valuable. The spectral analysis from OSIRIS confirmed the presence of hydrated silicate minerals across Bennu's surface. These are minerals, phyllosilicates specifically, including serpentines and saponites, that can only form in the presence of liquid water. They are not minerals that form from dry rock. Their presence on Bennu is direct evidence that at some point in Bennu's parent body's history, liquid water was present. Not on Bennu as it exists today, not in space, but inside the larger parent body, before the collision that shattered it, when the parent body was large enough to retain internal heat from radioactive decay and allow liquid water to exist in its interior, an environment called an aqueous alteration environment. In that environment, dry rock reacted with water to produce hydrated minerals. Those minerals were then preserved in the fragments that reaccumulated into Bennu and are present today on its surface. The water is gone, but its signature, written into the crystal structure of the minerals it left behind, survived 4.5 billion years. Then, in January 2019, something appeared in the navigation camera images that had not been predicted by any model. On January 6, 2019, image analysis software identified a cluster of bright moving dots in NavCam images taken during routine operations. The dots were moving outward from Bennu's surface. Particles were being ejected. A review of the preceding images found additional events, and more. By the end of systematic analysis, 19 separate particle ejection events had been documented between January and September 2019. In total, more than 200 individual particles were tracked, ranging from less than a centimeter to approximately 10 centimeters in size. Their trajectories varied. Most followed ballistic arcs. They launched off the surface, traveled outward into the space immediately around Bennu, and then fell back under Bennu's weak gravity within minutes to hours. Some entered temporary orbit around the asteroid, circling it for a period before eventually settling back to the surface. A small number escaped Bennu's gravity entirely and began independent heliocentric orbits. This behavior, an asteroid actively ejecting surface material, had never been observed before. The science team proposed several mechanisms. Thermal fracturing was considered the most likely primary cause. The extreme temperature cycling on Bennu's surface, from approximately 127 degrees Celsius at local noon to approximately -73 degrees Celsius in the middle of the night, a range of 200 degrees in a rotation period of just over 4 hours, would cause rocks to expand and contract repeatedly. Over time, the cycling cracks rocks along stress fractures. In some cases, the fragments produced are small enough and the cracks energetic enough to send particles off the surface. The timing of the ejection events was consistent with this explanation. Most events occurred in the morning hours of Bennu's short day, the period when the surface temperature is rising most rapidly, when the thermal stress gradient is steepest. Micrometeorite impacts, tiny particles from the interplanetary dust environment striking the surface at high velocity, were also proposed as a contributing mechanism. At Bennu's distance from the Sun, the flux of interplanetary dust is sufficient to produce small impacts regularly. Sublimation of volatile compounds near the surface. Water ice, or organic materials heated to the point of vaporization, was a third proposed mechanism. If a layer of volatile material exists just below the surface, solar heating could drive gas pressure sufficient to loft overlying particles. The exact mechanism or combination of mechanisms was not definitively resolved by the mission. Bennu was old, and it was active. It was a fossil from the beginning of the solar system that was still responding to the universe around it. The surface mapping campaign and boulder hazard assessment consumed most of 2019. The mission team cataloged every boulder above 38 centimeters in height, building a comprehensive hazard database that covered the entire surface. 4 candidate sample collection sites were identified and named for birds: nightingale in the northern hemisphere, kingfisher, osprey, and sandpiper nearer the equator and southern regions. Nightingale was selected as the primary sample site. Located at 56 degrees north latitude, within a relatively young impact crater 140 meters across, Nightingale contains some of the finest grained surface material visible anywhere on Bennu, exactly the material type that TAGSAM was designed to collect. The relative youth of the Nightingale crater surface, indicated by fewer superimposed smaller craters and less space weathering in the spectral data, suggested material less altered by long-term exposure to the space environment. But Nightingale was surrounded by boulders. The original safe zone requirement for sample collection had been a clear area 25 meters in diameter. No such area existed anywhere on Bennu. The mission team accepted a revised requirement, 8 meters. A circle 8 meters across. OSIRIS-REx, with solar panels deployed, measured 6.2 meters across. The margin between the spacecraft's edges and the boundary of the safe zone was approximately 90 centimeters on each side. To navigate to that precision, the team implemented a system called Natural Feature Tracking. NFT worked by comparing live camera images from the descending spacecraft to a preloaded terrain map, identifying specific boulders and surface features, and using those identifications to calculate the spacecraft's position relative to the target. If the computed position deviated from the planned approach beyond a defined threshold, the system would autonomously abort the descent and return the spacecraft to orbit. 2 rehearsal descents, one reaching 75 meters, one reaching 40 meters above the surface, refined the terrain model and tested the NFT system against real data. By October 2020, the mission team was as prepared as preparation could make them. The tag date was set for October 20th, 2020. On that day, OSIRIS-REx would descend from orbit, slow itself through a series of engine burns, extend the TAGSAM arm, and attempt to touch a surface that had last been disturbed by anything millions of years ago. In the control rooms at Lockheed Martin Space in Littleton, Colorado, and at the University of Arizona in Tucson, hundreds of people who had worked toward this moment for years took their positions. The descent began in the early morning hours of October 20th, UTC. The spacecraft fired its engines and began a slow arc toward the surface, traveling at 44 centimeters per second, slower than a walking pace. At 125 meters altitude, the Natural Feature Tracking System activated. At 75 meters, the TAGSAM arm extended. At 40 meters, the descent was committed. At approximately 2212 UTC, OSIRIS-REx made contact with the surface of Bennu at Nightingale Crater. The tagsum head pressed into the surface, the nitrogen charge fired, material stirred. The contact pad captured what the gas had lifted. 5 seconds. Then the thrusters fired, and OSIRIS-REx pushed itself away from the surface. The SAMCAM images showed something remarkable. The surface at Nightingale had not resisted the contact. The material had parted around the descending arm like a fluid, drawing the spacecraft 48 centimeters below the surrounding terrain before the thrusters arrested the motion. Material had billowed outward in slow-motion clouds, some of it capturing in the TAGSAM collection container, some of it drifting slowly back to the surface in the weak gravity. Bennu's surface, 4.5 billion years old, had behaved like water. The confirmation signal that contact had occurred and the spacecraft had backed safely away arrived at Earth at approximately 22:30 UTC, 18.5 minutes after the event itself. The mission team confirmed the sequence had completed. Days later, when they commanded the spacecraft to spin slowly to measure its rotational inertia, a technique for estimating sample mass, the number that came back suggested well over 200 grams had been collected. The minimum mission requirement was 60 grams. The spacecraft had collected more than 4 times the minimum. Whatever Bennu had given, it had given generously. OSIRIS-REx sealed the tagsum container, stowed the arm, and began preparing for a departure that would not come until May 2021. In the months between sample collection and departure, the science team continued studying Bennu, but the mission's defining act was complete. The spacecraft was carrying something that had not been on Earth for 4.5 billion years. Now came the long journey home. The 2-year orbital campaign following the TAG maneuver gave scientists time to absorb what OSIRIS-REx had done and what the telemetry data implied about the material it had collected. The images from SAMCAM, taken during and immediately after contact, showed something that became one of the most analyzed datasets in the mission's history. As the TAGSAM head pressed into Nightingale's surface, the surrounding regolith responded in slow motion, particles lifting gently away from the disturbance zone, spreading outward in thin arcs against the black of space, some falling back in lazy trajectories, some drifting away entirely. The material had almost no cohesion. It had yielded to the contact like a fluid. Analysis of the SAMCAM footage, combined with the depth measurement from the arm's position encoders, allowed scientists to estimate the mechanical properties of the Nightingale regolith. The material's bulk density was extremely low, on the order of 500 to 900 kilograms per cubic meter, consistent with a loosely packed aggregate of fine particles with substantial porosity even at the grain scale. In practical terms, the surface of Bennu at Nightingale was fluffier than talcum powder. 48 centimeters of depth penetration in that moment of contact, with forces governed by the tagsum design, implied a material with almost zero shear resistance, not soil in any ordinary sense, not sand. Something closer to the consistency of a pile of very fine, very dry snow, except that it had been sitting in space, exposed to vacuum and cosmic ray radiation for millions of years. The particle size distribution in the collected sample, which would later be formally characterized in laboratory analysis following the capsule's return, was expected to include material spanning from fine dust at the micrometer scale to small pebbles potentially a centimeter or more in firm-signed diameter. TAGSAM's filter system was designed to capture material across this range. Whether the nitrogen gas and 5-second contact window had captured a representative sample of Nightingale's surface, or had preferentially selected certain particle sizes, would be a question for the laboratory. The rotational inertia measurement, performed days after TAG, a spin maneuver that allowed ground controllers to estimate the added mass of the collected sample by comparing the spacecraft's rotational dynamics before and after collection, suggested that the total captured mass substantially exceeded the mission's 60-gram requirement. The best estimate at that point was approximately 250 grams. It would later be confirmed after Earth return at approximately 121 grams of loose material, with an additional 34 grams of fine dust distributed within the sample container, for a total of around 121 to 250 grams, depending on the measurement method. The uncertainty in the in-space measurement highlighted an important point. The most precise characterization of the sample had to wait for Earth. In space, mass can be estimated through inertia measurements, but the estimates carry significant uncertainty. In a laboratory, with precision scales and a controlled environment, the actual mass could be determined to within a few milligrams. The first direct mass measurement would happen in September 2023. Until then, the collected material traveled in its sealed container inside OSIRIS-REx as the spacecraft prepared to leave Bennu. In May 2021, the mission team uploaded the departure commands. OSIRIS-REx fired its engines and began climbing away from Bennu on a trajectory that would, over the following 2.5 years, carry it on a looping orbit back toward Earth's vicinity. The asteroid receded in the spacecraft's cameras. Bennu, 490 meters across, 73 billion kilograms, 4.5 billion years old, slowly shrank to a point of reflected light. The spacecraft was on its way home. The sample capsule was sealed. The arm was stowed. And OSIRIS-REx, carrying something it had collected in 5 seconds from a surface 4.5 billion years old, began the long work of waiting. The departure from Bennu was not immediate. Between the TAG maneuver in October 2020 and the engine burn that would begin the journey home, the spacecraft remained in the vicinity of Bennu for more than 6 months. During that period, the science team continued collecting data, not because the sample collection had left anything undone scientifically, but because the additional observation time was too valuable to waste. The post-TAG period produced some of the most detailed mapping data of the mission. With the pressure of the sample collection event behind them, the science team could focus entirely on building the most complete picture of Bennu that would ever be assembled. OLA completed its topographic survey of the northern hemisphere in full. Polycam imaged the Nightingale crater in extraordinary detail following the TAG event, documenting the disturbance caused by the TAGSAM contact, the crater left by the sinking arm, the displacement of surface material. The images showed a roughly circular disturbance zone, approximately 8 meters across, with material that had been compacted or pushed aside, visible around the edges. The subsurface material exposed by the TAG contact was brighter than the surrounding surface. This brightness difference, subtle but measurable in the color-corrected MapCam images, indicated that the material just below Nightingale's surface had been less exposed to the space environment than the surrounding terrain. Less space-weathered, more pristine. The contact had inadvertently opened a window into material that had not seen sunlight or the solar wind in millions of years. The OSIRIS spectrometer observed the disturbed zone during subsequent low-altitude passes. The spectral signature of the newly exposed material showed stronger absorption features associated with hydrated silicates than the surrounding, more space-weathered surface. The water-bearing minerals that had been identified across Bennu's surface generally appeared more concentrated, more spectrally pronounced in the freshly exposed material beneath. This suggested a surface process at work over geological time, slow modification of the uppermost layer by space weathering, producing a surface that is chemically different from the material just centimeters beneath it. And it reinforced the mission's scientific rationale. The sample TAGSIM had collected was not just surface dust altered by billions of years of solar exposure. It included material from depth, material that had been protected by the overlying surface layer from the space environment, material closer to its original state at the time of formation. On May 10, 2021, OSIRIS-REx fired its main engine for 7 minutes, executing the departure burn that would begin the journey home. The delta V, the change in velocity, imparted by the burn was approximately 964 meters per second. On a spacecraft weighing 880 kilograms at that point in the mission, most of the launch propellant had been consumed. That thrust produced a significant trajectory change, enough to place OSIRIS-REx on a path that would intercept Earth's orbital position in September 2023. The journey home would take approximately 2.5 years. For most of that time, nothing happened that required active control. OSIRIS-REx was in cruise mode, solar panels oriented toward the sun, science instruments largely powered down, the navigation team monitoring trajectory and making occasional small correction burns to keep the spacecraft on its planned path. The sample container inside the spacecraft, sealed in the TAGSAM canister, traveled through interplanetary space in conditions close to those it had experienced on Bennu, cold, dark, and in vacuum. The temperature inside the TAGSAM container during the cruise home was estimated at approximately -10 to -30 degrees Celsius, cold enough to suppress any chemical reactions that might alter the sample, but not cold enough to cause any physical damage to the collected material. The scientists waiting on Earth could not open the container. They could not measure what was inside. They could not verify that the nitrogen gas had stirred loose the material rather than compacting it. They could not confirm what minerals were present, what organic compounds might be there, what the particle size distribution looked like. They could only wait. 2.5 years, a spacecraft the size of a passenger van, alone in interplanetary space, carrying 250 grams of material that might contain evidence for how life began on Earth. The waiting ended on September 24th, 2023. At approximately 10:52 UTC on that morning, the OSIRIS-REx sample return capsule, a roughly 1-meter diameter heat-shielded re-entry vehicle containing the sealed TAGSAM canister, separated from the spacecraft bus and began its final approach to Earth. The separation occurred at an altitude of 102,000 kilometers above Earth's surface. 4 hours later, the capsule entered Earth's atmosphere. It hit the upper atmosphere at approximately 44,500 kilometers per hour, about 12.4 kilometers per second. At that velocity, the aerodynamic compression of the air ahead of the capsule generated temperatures at the heat shield surface of approximately 2,760 degrees Celsius. The ablative carbon phenolic heat shield, a material that chars and erodes in a controlled manner, carrying heat away from the capsule as it ablates, protected the sample container from these temperatures. The capsule decelerated rapidly through the upper atmosphere, the drag of the thickening air converting its kinetic energy into heat. A drogue parachute deployed at 32 kilometers altitude, slowing the capsule further. A main parachute deployed at 3 kilometers altitude, reducing the terminal descent velocity to 4.5 meters per second. The landing zone was the Utah Test and Training Range, a remote military facility in the western Utah desert, an expanse of flat, arid terrain where the risk of the capsule landing on populated areas or sensitive ecosystems was minimal, and where helicopter-borne recovery teams could reach it quickly. At approximately 10:52 local time in Utah, 1652 UTC, the capsule touched down on the desert surface. The recovery teams reached it within minutes. The sample had arrived. The first step after landing was not to open the container, it was to take the temperature. Recovery teams used non-contact infrared thermometers to verify that the external surface of the capsule had cooled sufficiently from the re-entry heating, ensuring that no thermal damage to the sample had occurred. They checked the integrity of the parachute connections, documented the landing position with GPS, and photographed the capsule from multiple angles in its undisturbed state. Then it was loaded carefully into a specially designed transport container and airlifted by helicopter to a temporary cleanroom facility assembled at the landing range. The cleanroom, a portable structure erected specifically for this purpose, maintained a positive pressure environment using filtered nitrogen gas, preventing any contamination of the sample by Earth's atmosphere. Oxygen, water vapor, and biological material from Earth's environment could all potentially react with or contaminate pristine asteroid material, altering its chemistry and compromising the scientific value of the sample. The TAGSAM canister was removed from the heat shield assembly, placed in a sealed nitrogen-purged bag, and placed inside a specially built transport container with its own internal nitrogen atmosphere. It was then transported by aircraft to NASA's Johnson Space Center in Houston, Texas, home of the Astromaterials Research and Exploration Science Division, which manages the curation of all extraterrestrial samples returned by NASA missions, including the Apollo lunar samples, interplanetary dust collected by high-altitude aircraft, comet material from the Stardust mission, and solar wind material from the Genesis mission. The OSIRIS-REx sample joined this collection, but not yet as an open container. The formal processing of the TAGSAM canister began over the following days in a specially built curation facility at Johnson Space Center, a room designed specifically for this mission, constructed years before the capsule's return, with materials chosen to avoid contamination of the sample by industrial compounds, cleaning agents, or biological material. The first task was documentation. Before anything inside the TAGSAM container was touched, photographed, or analyzed, the team carefully cataloged everything visible on the exterior of the mechanism, the outer surface of the contact pad, the filter screens visible through the openings, and the condition of the mechanical components. What they found on the exterior was immediately significant. A black, fine-grained material was visible on the exterior surfaces of the TAGSAM mechanism, on the contact pad, on the screens, on the interior of the lid assembly. This was material that had been collected during the TAG event and had not been fully captured by the interior filter system. Some had settled on accessible surfaces during the approach to Earth, and some had been present since the contact itself. This exterior material was carefully collected first, using specialized tools developed for the mission, and stored separately from the interior sample. The total mass of this exterior material, collected from surfaces that were accessible before the interior canister was opened, was approximately 34 grams of fine dust and fragments. Then, in October 2023, the team began the process of opening the TAGSAM canister itself. The mechanism had been designed for ease of operation in space, under vacuum and in microgravity, using tools operated by the spacecraft's robotic arm. Opening it in a terrestrial glove box environment, under nitrogen atmosphere, with human hands inside gloves reaching through sealed ports, presented unexpected mechanical difficulties. Two of the TAGSAM lid fasteners did not respond as expected to the specially designed tools. The standard procedure was paused. Engineers consulted. New tools were fabricated. A spacecraft had traveled 2 billion kilometers and returned safely to Earth, and the final obstacle was 2 stubborn screws. The modified tools worked. By the second week of October 2023, the TAGSAM canister was open. Inside was darkness at first, the black material that had been predicted. Dark, fine-grained, carbon-rich regolith from the surface of asteroid Bennu. The initial mass measurement of the interior sample, performed using precision scales under the nitrogen atmosphere of the curation glove box, came in at approximately 70 grams. Combined with the exterior material, the total collected mass exceeded 121 grams, nearly double the mission's minimum requirement of 60 grams. Later, more thorough collection and measurement of material within the container mechanism itself would bring the confirmed total higher still, ultimately to approximately 121.6 grams of loosely consolidated material, not counting material embedded in the filters and screen that would require more invasive processing to extract. The mission team had collected more than twice the minimum requirement from a single brief contact on a boulder-strewn asteroid 300 million kilometers from Earth. Now the scientific analysis could begin. The Johnson Space Center curation team began distributing small aliquots, measured subsamples of the Bennu material to science teams around the world. The distribution followed established protocols developed over decades of curating Apollo lunar samples and other returned materials. Each aliquot is tracked by weight, location of origin within the sample container, and the processing steps it has undergone. The documentation ensures that the provenance of every analysis result is unambiguous. The initial science results began emerging within weeks. The first confirmed finding, announced publicly in October 2023, was the presence of water-bearing clay minerals, specifically phyllosilicates, including serpentine and saponite, in the Bennu sample. This was not a surprise. OSIRIS had detected the spectral signatures of hydrated silicates across Bennu's surface from orbit, but the confirmation in hand sample, with laboratory analysis rather than remote spectroscopy, established the finding with a new level of certainty. These minerals require liquid water to form. Their presence in Bennu's material is direct evidence that liquid water existed in Bennu's parent body, the larger asteroid from which Bennu was derived, sometime in the first few 100 million years of solar system history, when the parent body was large enough to retain internal heat from the decay of short-lived radioactive isotopes such as aluminum-26. Aluminum-26 has a half-life of approximately 717,000 years. It was present in the solar system's earliest solid materials, incorporated from the remnants of a nearby supernova explosion that may have helped trigger the collapse of the solar nebula in the first place. As it decayed inside early planetesimals, small bodies that would eventually grow into the planets or be fragmented into asteroids, its energy heated their interiors. In bodies large enough to retain this heat, liquid water existed in the interior, reacting with dry silicate rock to produce the phyllosilicates now found in Bennu's sample. The water that altered these minerals has been gone for more than 4 billion years, but the minerals themselves, the stone record of that ancient water, survived intact, collected from an asteroid, returned to Earth, and now sit in a laboratory in Houston. Carbon was also confirmed in the initial analysis, not just as a trace element, but as a significant component of the sample. The carbon content of the Bennu material is consistent with the most carbon-rich meteorite types known, including the CI chondrites, which are considered the most chemically pristine solar system materials available for study on Earth. CI chondrites have an elemental composition that closely matches the composition of the Sun's photosphere, a correspondence that has long been interpreted as evidence that they formed from the same primordial material as the Sun itself, with minimal processing since the earliest epoch of solar system formation. If Bennu's sample falls into or near the CI chondrite compositional range, it represents one of the most primitive samples of solar system material ever studied in a laboratory. The organic chemistry of the Bennu sample attracted particular scientific attention. Organic molecules, carbon-based compounds, are present across the universe in a wide range of environments, from the atmospheres of giant planets to the surfaces of comets to the gas clouds between stars. But the specific organic molecules relevant to the origin of life are a subset of this broader class, the molecules that, under the right conditions, can participate in the chemical reactions that produce amino acids, nucleobases, sugars, and ultimately the complex polymers, proteins, and nucleic acids that form the molecular basis of all known life. These molecules include amino acid precursors, nitrogenous bases related to the components of RNA and DNA, and a class of compounds called polycyclic aromatic hydrocarbons. They have been detected in carbonaceous meteorites for decades, most famously in the Murchison meteorite, which fell in Victoria, Australia in 1969, and which has been found to contain more than 70 different amino acids, most of them not present in terrestrial biochemistry. The Bennu sample offered a fresh opportunity to study these compounds in material that, unlike any meteorite, had been protected from terrestrial contamination since the moment of collection. Every meteorite that falls through Earth's atmosphere and lands on the surface is immediately exposed to Earth's biological and chemical environment. Even meteorites recovered within hours of their fall, carefully handled, stored in controlled conditions, have experienced some degree of terrestrial contamination simply from contact with Earth's atmosphere. The amino acids and organic compounds found in meteorites are always studied against a background of potential contamination from Earth's own rich organic chemistry. The Bennu sample was different. It had been collected in space, sealed in space, transported in a sealed container, and processed in a nitrogen atmosphere that excluded Earth's biological environment. Any organic compounds found in it could be attributed to Bennu itself with a much higher level of confidence than has ever been possible for any meteorite analysis. This is why the returned sample changes things. Not just the quantity of material. Any large meteorite provides more than 121 grams, but the chain of custody, the certainty of provenance, the absence of the terrestrial contamination problem that haunts every meteorite analysis. The initial organic chemistry results from the Bennu sample, presented at scientific conferences in late 2023 and early 2024, confirmed the presence of a rich suite of organic compounds, including dozens of amino acids, many of which are also found in the Murchison meteorite, as well as a variety of other nitrogen-bearing organic compounds. The amino acids identified included several of the 20 standard amino acids used in terrestrial proteins, glycine, alanine, valine, and others, as well as numerous non-standard amino acids not present in Earth's biochemistry. The presence of both standard and non-standard amino acids is scientifically informative. Standard amino acids are the ones used by life on Earth. They are also produced by abiotic chemistry, by non-biological chemical reactions in the right environments. Finding them in an asteroid sample does not prove biological origin. What it demonstrates is that the chemistry that produces these molecules operates outside of Earth, in the early solar system environment. Non-standard amino acids, ones that life on Earth does not use, are in some ways even more informative. They demonstrate that the amino acid production in the early solar system was not specifically tuned to the particular subset of amino acids that life on Earth eventually selected. The chemistry was broader. Life, when it emerged, used a specific selection from a larger chemical library. That library, the Bennu sample suggests, was delivered to the early Earth in materials similar to Bennu during the period of intense asteroid and comet bombardment in the first few 100 million years of Earth's history. The specific mechanism by which asteroid delivered organics might have contributed to the origin of life on Earth is not settled science. Several hypotheses exist. One holds that the organics delivered by asteroid impacts provided the raw chemical building blocks that in the warm chemical environments of early Earth's oceans, hydrothermal vents, or evaporating tidal pools underwent further reactions that produced the polymers necessary for life. Another holds that asteroid impacts delivered not just organic molecules, but also liquid water, the medium in which these reactions could occur, through the water, ice, and hydrated minerals carried by carbonaceous asteroids. A third, more speculative possibility holds that some of the chemical complexity required for life was assembled not on Earth but in space, in the aqueous environments of asteroid parent bodies, like the one that produced Bennu, and that the material delivered to early Earth was already more chemically complex than simple organic molecules. None of these hypotheses has been definitively confirmed. The origin of life remains one of the fundamental open questions in science. But the Bennu sample has added something precise and irreplaceable to this conversation: the most pristine, least contaminated sample of primitive solar system organic chemistry ever studied in a laboratory on Earth. The question of how life began does not have an answer yet, but the materials that Bennu carried have been present in the solar system since before the Earth formed. They were here before any ocean existed, before any continent, before any atmosphere, and now, in a laboratory in Houston, Texas, scientists are reading the chemistry of the beginning of the solar system, looking for the sentence that started everything. The mineralogical analysis of the Bennu sample extended beyond the phyllosilicates and organic compounds to a broader characterization of the full mineral assemblage. The sample contains magnetite, iron oxide, in a form consistent with formation in an aqueous environment. It contains carbonates, including magnesium and calcium carbonate, also consistent with aqueous alteration. It contains sulfides, and it contains a diversity of silicate minerals in various states of alteration, providing a detailed record of the thermal and chemical history of Bennu's parent body. One finding from the mineralogical analysis carried particular significance for planetary defense considerations. The mechanical properties of the Bennu surface material, the extreme looseness, the low bulk density, the near-zero shear strength revealed by the tag contact, have direct implications for understanding how a Bennu-like asteroid would respond to a deflection attempt. Planetary defense strategies for potentially hazardous asteroids include several approaches, depending on the lead time available. If decades are available, a gravitational tractor, a spacecraft hovering near the asteroid and using its gravitational attraction to gradually pull the asteroid off its course, could be employed. If years are available, a kinetic impactor, a spacecraft deliberately colliding with the asteroid at high velocity, could change its velocity sufficiently to alter its orbit. The kinetic impactor approach has been tested. In September 2022, NASA's DART mission, the Double Asteroid Redirection Test, impacted the moonlet Dimorphos of the binary asteroid system Didymos at approximately 6.1 kilometers per second, successfully changing Dimorphos's orbital period around Didymos by approximately 33 minutes, significantly more than the predicted minimum of 73 seconds. But the effectiveness of a kinetic impactor depends critically on the mechanical properties of the target. A rubble pile, like Bennu, responds to an impact very differently from a monolithic rock. When a kinetic impactor strikes a solid body, the momentum transfer is relatively direct. The impactor's momentum is transferred to the target, and the ratio of crater excavation to momentum change, called the momentum enhancement factor, or beta, is relatively predictable. When a kinetic impactor strikes a rubble pile, the loose material can absorb and dissipate energy differently. The ejecta, material blown outward from the impact crater, plays a crucial role in enhancing the momentum transfer beyond the impactor's own momentum. In a loosely aggregated body, the ejecta dynamics may be different from those of a coherent rock. The mechanical characterization of Bennu from OSIRIS-REx, the 40% porosity, the near-zero surface cohesion at Nightingale, the fluid-like response to the tag contact, will be incorporated into models of how a Bennu-sized rubble pile would respond to a kinetic deflection attempt. This is not abstract science. If, as the trajectory calculations refine over the coming decades, the probability of a 2182 Bennu impact remains non-negligible, the information OSIRIS-REx gathered will be directly relevant to any decision about intervention. The spacecraft was, in this sense, a reconnaissance mission. It went to Bennu not only to understand the past, the chemistry of the early solar system, but to understand the future, how to change the trajectory of a rock that 4.5 billion years after it formed is considering returning. The comparison between the Bennu sample and previously studied carbonaceous chondrite meteorites was not simply a matter of confirming what had already been found in meteorites. It was a study in the limits of what meteorites can tell us. Every carbonaceous chondrite meteorite in scientific collections arrived on Earth through the same path, It entered the atmosphere at high velocity, experienced extreme heating during atmospheric transit, landed somewhere on Earth's surface, and was then exposed to Earth's environment for some period before recovery. Some meteorites are recovered within hours. Others are found in Antarctic ice fields, where the combination of cold, dry conditions and slow ice movement has preserved them for thousands of years. A few have been recovered in desert environments where the lack of liquid water has slowed chemical alteration, but none of them were collected in space and returned under controlled conditions. The contamination issue matters more for some types of science than others. For mineralogy, studying the silicate minerals, the carbonates, the oxides, terrestrial contamination is significant but manageable. Terrestrial minerals have characteristic compositions that differ from those formed in space, and careful analysis can identify and exclude contamination. For organic chemistry, the problem is far more severe. Earth's surface is saturated with organic compounds of biological origin. Every cubic centimeter of soil contains billions of microorganisms. Every raindrop carries dissolved organic carbon from the atmosphere. The surfaces of desert rocks are coated with thin biological films. Even in the most carefully controlled laboratory environments, trace organic contamination from the researchers themselves, from the air, from surfaces, is a constant challenge. When scientists find amino acids in a carbonaceous meteorite, they must always ask, are these amino acids from the asteroid, or are they Earth contamination that entered during the atmospheric transit, during landing, during storage, during handling? Analytical techniques can partially address this question. The ratio of left-handed to right-handed versions of amino acid molecules, their chirality, provides information. Life on Earth uses exclusively left-handed amino acids, so an excess of non-standard chirality might indicate extraterrestrial origin. The isotopic composition of carbon and nitrogen in organic compounds can also distinguish terrestrial from extraterrestrial material. But these techniques are statistical and interpretive, not definitive. With the Bennu sample, the contamination question is answered differently. The collection was clean, the transport was sealed, the processing was controlled. The organic chemistry found in the Bennu sample was on Bennu before the spacecraft arrived. This distinction, subtle in its description, profound in its scientific implications, is why the return sample was worth the cost and complexity of the OSIRIS-REx mission in a way that the study of meteorites, however valuable, could not replace. The comparison with the Hayabusa 2 mission's sample from asteroid Ryugu adds another dimension. Hayabusa 2, operated by the Japan Aerospace Exploration Agency, visited the carbonaceous asteroid Ryugu between 2018 and 2019. It collected 5.4 grams of surface material through a touch-and-go collection method, similar in concept to TAGSAM, and returned that material to Earth in December 2020, 3 years before OSIRIS-REx's capsule arrived. The Ryugu sample has been studied intensively and has produced landmark results: confirmation of amino acids, detection of uracil, one of the 4 nucleobases of RNA, and a rich assemblage of organic compounds that closely parallels what has been found in meteorites, but with the added certainty of controlled sample return. Bennu and Ryugu are both B-type or CG-type carbonaceous asteroids, broadly similar in spectral classification, and both appear to be rubble pile aggregates of primitive material. The comparison between their samples now both in laboratory analysis, offers something unprecedented in planetary science: a controlled comparison of two primitive asteroid samples, both returned under controlled conditions from two bodies with similar broad classifications but different specific properties. If the organic chemistry of Bennu and Ryugu are similar, it strengthens the case that carbonaceous asteroids broadly carry this type of chemistry, that the delivery of organics to the early Earth was not a singular event dependent on one specific body, but a widespread process operating across a population of similar objects. If the chemistry differs in specific ways, it provides information about the diversity within the carbonaceous asteroid population and about the factors, perhaps differences in the depth of aqueous alteration, or differences in thermal history, or differences in the composition of the parent body, that produce different chemical outcomes from similar starting conditions. Early comparative results suggested that Bennu and Ryugu share broad similarities but differ in some mineralogical details, consistent with origin from related but distinct parent bodies, or from different regions of the same parent body at different times. The analysis is ongoing. Two samples from two asteroids returned from space within 3 years of each other, being compared in laboratories on opposite sides of the planet. This is what the science looks like when it is working at its edge. The story of Bennu does not end with the sample return. The spacecraft that collected the material, the bus, the propulsion system, the science instruments, the solar panels and attitude control thrusters and navigation systems, was not brought home. It could not be. The capsule was designed to enter the atmosphere. The spacecraft was not. When the tungstim canister separated and the capsule began its final descent, OSIRIS-REx executed a divert maneuver, firing its thrusters to change its own trajectory away from Earth. It would not be destroyed. It had been given a new mission. The extended mission was named OSIRIS-APEX, the Apophis Explorer. Its target, Asteroid 99942 Apophis. Apophis is in the planetary defense community, perhaps the most discussed asteroid in history. Discovered in June 2004, its initial orbital calculations produced something that made planetary scientists worldwide take immediate notice: a probability of Earth impact in 2029 that briefly reached as high as 2.7%, higher than any previously cataloged near-Earth asteroid. The 2029 scenario was quickly ruled out as additional observations refined the orbit. Then the concern shifted to 2036. That was ruled out as well, with even more precise observations. For Apophis, unlike Bennu, the trajectory calculations are now sufficiently precise that a 2036 impact is considered essentially impossible. The remaining impact scenarios extend further into the future, with probabilities that are extremely small. But 2029 retains extraordinary scientific interest. On April 13, 2029, Apophis will pass Earth at a distance of 31,600 kilometers from Earth's surface. This is closer than the geostationary orbit belt, where most communications satellites operate, at 35,786 kilometers altitude. It will be the closest approach of a catalogued asteroid of this size, roughly 370 meters, in recorded history. At that distance, Apophis will be visible to the naked eye from parts of Europe, Africa, and Asia, a point of moving light crossing the sky at measurable angular velocity, visible without any optical aid, the closest a known hazardous asteroid has come to Earth in modern times. It will also pass through a gravitational keyhole region. The 2029 encounter will be observed in unprecedented detail by telescopes around the world and potentially by dedicated spacecraft. The gravitational perturbation it experiences will alter its orbit in ways that current measurements cannot fully predict in advance, creating a residual uncertainty about impact scenarios in 2068 and beyond. OSIRIS-REx is traveling to Apophis to be in position for the 2029 encounter and to observe the asteroid from close range before, during, and after the Earth flyby. The spacecraft is expected to arrive at Apophis 6 weeks before the April 2029 encounter, allowing it to characterize the asteroid in detail before the Earth approach. During the flyby itself, OSIRIS-REx will observe how Earth's gravity affects Apophis, potentially causing landslides and surface disturbances on an asteroid that has never in its recent history experienced a gravitational force of this magnitude. Earth's gravity, acting on a rock that is passing closer than our satellites, will be strong enough to change the surface of that rock in real time, and a spacecraft will be watching. After the flyby, OSIRIS-REx will continue operating at Apophis, studying the changes the Earth encounter produced, characterizing its mineralogy, and potentially conducting a surface disturbance maneuver similar to the TAG event at Bennu, not to collect a sample, but to expose subsurface material and observe its properties. The mission's science will extend the knowledge gained at Bennu to a second near-Earth asteroid, building a comparative database that will inform both planetary science and planetary defense for decades. The OSIRIS program is in this sense still active. It did not end in the Utah desert in September 2023. It is continuing on a spacecraft that left Bennu in 2021 and is currently in transit across the inner solar system, scheduled to arrive at one of the most closely watched asteroids in human history. What Bennu revealed about the chemistry of the early solar system, the water-bearing minerals, the organic compounds, the carbons, represents one chapter in an ongoing investigation. The same mission architecture, extended to a different target, will add another. The science that began with a flagged object in the linear survey data in September 1999 is still in progress. Meanwhile, the material from Bennu continues to be analyzed. The initial distribution of samples to research teams around the world, the first formal allocation in June 2024, with subsequent allocations planned over years and decades, is designed to ensure that the scientific return from the mission extends long beyond the initial publication rush. Apollo lunar samples collected in the 1960s and 1970s are still being analyzed today, with new analytical techniques revealing information that was inaccessible to the instruments available at the time of collection. The same will be true of the Bennu sample. Techniques that do not yet exist will be applied to this material in 20 years, in 50 years, asking questions that scientists in 2024 have not yet thought to ask. The sample is not just a scientific resource for today, it is a time capsule sent forward, material from the beginning of the solar system, now in a laboratory on Earth, waiting to be understood by science that hasn't been invented yet. The scientific questions the Bennu sample bears on extend in multiple directions simultaneously. The question of the origin of life on Earth, the question of how the solar system formed and evolved in its earliest period, the question of how carbonaceous asteroids are distributed through the inner solar system, and what role they played in delivering water and organic material to the terrestrial planets. The question of how to deflect a hazardous asteroid. These questions are not separate. They are connected through the same material, the same carbon-rich, water-altered ancient rubble that collected over 4.5 billion years of solar system history into a roughly spheroidal body 490 meters across that spent 4.5 billion years orbiting the sun, that a spacecraft visited, briefly touched, and brought a small piece of home. The number 490 meters is easy to say, but held in mind for a moment, it has a specific physical reality, a body half a kilometer across, roughly the distance from one end of a city block to the other, composed of rock and dust, 4.5 billion years old, orbiting a star 1 astronomical unit away, with a 1 in 2,700 chance of striking the planet on which that star's chemistry eventually gave rise to the organisms that built the spacecraft that went there. That trajectory, from the collapse of a solar nebula 4.56 billion years ago to a clean room in Houston, Texas in 2023, is one of the longest unbroken chains of physical causation in any story science has been able to tell. And the chain is not finished. Bennu is still out there. There is a broader context to Bennu that the mission's specific findings sit within, the history of how scientists came to understand the role of small bodies in shaping the planets. For most of the 20th century, the dominant narrative of solar system formation was one of gradual accumulation, dust grains colliding and sticking to form pebbles, pebbles forming rocks, rocks forming planetesimals, planetesimals growing through continued collisions into protoplanets, and eventually the planets themselves. In this picture, the early solar system was a violent but ultimately constructive process, with material steadily consolidating into larger and larger bodies under the pull of gravity. The role of small bodies in this picture was largely that of building material, the raw feedstock that the planets consumed on their way to their current sizes. What the late 20th and early 21st centuries of solar system science revealed was a more complex picture. The terrestrial planets, Mercury, Venus, Earth, and Mars, formed in the inner solar system in a region relatively depleted of water and organic material. The temperatures in the inner solar system during planet formation were high enough that volatile compounds, water, carbon dioxide, organic molecules, could not easily condense into solid form. The inner solar system's building blocks were predominantly silicates and metals. But the Earth has abundant water. Its surface is 70% ocean, and life, as far as we know, requires liquid water. Where did Earth's water come from? This question has been one of the central puzzles of planetary science for decades. The prevailing answer, supported by isotopic evidence, is that a significant fraction of Earth's water was delivered by carbonaceous asteroids and comets from the outer solar system, bodies that formed at distances from the Sun where water ice could condense and that were subsequently perturbed into the inner solar system by gravitational interactions with the giant planets. The ratio of deuterium to hydrogen, the D/H ratio, in Earth's oceans is the primary evidence for this conclusion. Deuterium is a heavy isotope of hydrogen. The D/H ratio in different water reservoirs carries a fingerprint of where and when that water formed. Earth's ocean D/H ratio matches most closely the D/H ratio measured in carbonaceous chondrite meteorites, and by extension in carbonaceous asteroids like Bennu. Comets, by contrast, tend to have higher D/H ratios than Earth's oceans, though with significant variability. The implication is that carbonaceous asteroids, not comets, were the primary water delivery mechanism for early Earth. If this interpretation is correct, then material like Bennu's was once falling into the early Earth in enormous quantities, not in isolated impacts, but in a sustained bombardment, the tail end of the accretion process, when the inner solar system was still being swept clean of the residual small body population. Every ocean on Earth, every river, every drop of water in every living cell on this planet. Some fraction of it arrived the way Bennu's material arrived at the Johnson Space Center, falling out of the sky. The timing of this delivery is constrained by a feature of the early solar system's history called the Late Heavy Bombardment, or the Lunar Cataclysm, a period around 3.9 billion years ago, recorded in the heavily cratered surfaces of the Moon, Mercury, and Mars, when the impact rate in the inner solar system appears to have been substantially elevated. The cause of the late heavy bombardment is debated. One influential model, the NICE model, developed in the early 2000s by a group of planetary scientists working in Nice, France, proposed that the late heavy bombardment was triggered by a gravitational resonance between Jupiter and Saturn that destabilized the outer solar system and sent a large population of small bodies inward. If the NICE model is correct, the late heavy bombardment delivered carbonaceous material, water and organics, to the early Earth at a time when the planet's surface was cooling, liquid water was becoming stable, and the chemical conditions for the origin of life were being established. This material, Bennu's sample, is a fragment of that delivery mechanism. Not from the late heavy bombardment itself, Bennu is a fragment of an asteroid that was shattered much more recently in geological terms, but it is made of material from the same population, carbonaceous bodies from the outer part of the asteroid belt, rich in water and organics that have been intermittently perturbing inward toward Earth for billions of years. Understanding this material in detail, understanding its chemistry, its mineralogy, its mechanical properties, its trajectory, is not merely scientific curiosity. It is an attempt to read the record of the process that made Earth habitable. The distance from a solar nebula 4.56 billion years ago to a sample curation laboratory in Houston is measured not just in space, but in time, and in the slow accumulation of scientific understanding across generations of researchers who will never meet, will never share a conversation, but will share the data flowing from a single moment of contact between a robotic arm and an ancient surface. That is what the OSIRIS-REx mission carried home. Not just 121 grams of dark dust and pebbles, but a question asked by a civilization that has barely begun to understand its own origins, addressed to material that was present before those origins were possible. The material is patient. It has been waiting 4.5 billion years already. It will wait a little longer while the science catches up. The isotopic record in the Bennu sample adds precision to this picture. Isotopes are variants of the same element with different numbers of neutrons in their atomic nuclei, because different processes, nuclear reactions in stars, radioactive decay, chemical fractionation, produce characteristic isotopic ratios. The isotopic composition of a sample carries a fingerprint of its history. Carbon isotopes record organic chemistry. Oxygen isotopes record the temperature at which minerals formed. Nitrogen isotopes carry signatures of the molecular cloud from which the solar system collapsed. The Bennu sample, analyzed for its isotopic composition, provides a multidimensional signature of where and when its material formed, a record written in atomic ratios that billions of years of geological processing on a planet could not have preserved. Pre-solar grains, tiny mineral particles that formed inside stars before the sun existed, incorporated into the solar nebula and survived into asteroids like Bennu without being melted or chemically altered, have been found in carbonaceous meteorites and are expected in the Bennu sample as well. Their isotopic compositions carry signatures from specific types of stars: red giants, asymptotic giant branch stars, core collapse supernovae. They are, in a precise sense, older than the solar system, material from stars that lived and died before the sun was born. In the Bennu sample, there may be dust from a star that no longer exists, material formed inside a nuclear furnace that burned out billions of years before the Earth formed, preserved inside a small dark rock that has been orbiting the sun in silence ever since. The laboratory in Houston is reading the ashes of dead stars. The scale of that is difficult to hold in mind all at once, but it is real, it is measured, and it is sitting in a container less than 30 centimeters across in a building in Texas, waiting for the next analytical technique to reveal the next layer of what it carries. The sample allocations from OSIRIS-REx began formally in June 2024. NASA's curation protocols for returned extraterrestrial samples follow a model developed over decades of managing Apollo lunar material, a model built on the recognition that the scientific value of a unique sample increases over time as analytical techniques improve, and that responsible stewardship means distributing carefully measured subsamples to research teams while preserving the majority of the material for future analysis. Of the approximately 121 grams of confirmed Bennu sample, the initial allocation released roughly a quarter to the broader scientific community. The remainder is being held in controlled curation at Johnson Space Center in nitrogen-purged containers at stable temperatures, available for future researchers using technologies that do not yet exist. The allocation process is competitive. Research teams submit proposals describing the specific scientific questions they intend to address, the analytical techniques they will use, the amount of sample required, and the facilities they have available. A peer review panel evaluates the proposals against criteria of scientific merit, analytical capability, and efficient use of a finite and irreplaceable resource. The first allocation cycle produced more than 200 approved proposals from research groups in the United States, Japan, Canada, the United Kingdom, France, Germany, and other countries, representing the broadest international scientific response to an asteroid sample in history. Each approved team receives a measured aliquot, typically milligrams to tens of milligrams for most analyses, with larger allocations for techniques that require more material. Every sample is tracked in a database that records its weight, its position within the sample container at the time of removal, and every analytical procedure it has subsequently undergone. This documentation is not bureaucratic formality, it is scientific infrastructure. When a finding from one laboratory needs to be compared against a finding from another, the question of whether the two aliquots came from the same region of the taxon container, and therefore potentially from the same region of the Nightingale crater floor, matters for interpreting any differences in their chemistry. The same handful of material, divided into hundreds of subsamples, being studied simultaneously by hundreds of scientists on multiple continents, each looking for a different aspect of the same 4.5 billion year record. The analytical techniques being applied to the Bennu sample span an extraordinary range. Scanning electron microscopy with energy dispersive X-ray spectroscopy allows scientists to image individual mineral grains at the micrometer scale and determine their elemental composition from the characteristic X-ray energies they emit when struck by the electron beam. Individual crystals of serpentine, saponite, and magnetite can be studied grain by grain, documenting the textural relationships between minerals that formed at different times and under different conditions. Transmission electron microscopy pushes resolution further to the nanometer scale, where the crystal structure of individual mineral phases can be directly imaged. At this scale, the defects, dislocations, and compositional gradients within individual mineral grains carry information about the temperatures and pressures at which they formed and the processes they subsequently experienced. Secondary ion mass spectrometry, SIMS, allows isotopic measurements at the micrometer scale. A beam of ions sputters material from the surface of a sample, and the ejected atoms are analyzed by mass spectrometry to determine their isotopic composition. This technique is used to hunt for pre-solar grains, the ancient stellar dust particles with anomalous isotopic signatures within the mineral matrix of the sample. Each presolar grain identified carries a fingerprint of the specific type of star in which it formed. Gas chromatography mass spectrometry, combined with liquid chromatography mass spectrometry, is used for organic chemistry analysis, separating and identifying the complex mixture of organic compounds in the sample, measuring their abundances, and determining the structural characteristics of individual molecules. Nuclear magnetic resonance spectroscopy provides information about the three-dimensional structure of organic molecules and the bonding environments of individual atoms within them. Synchrotron X-ray tomography allows non-destructive three-dimensional imaging of individual sample particles, revealing their internal structure, the distribution of different mineral phases within them, and the presence of voids or inclusions without consuming any of the irreplaceable material. Each technique reveals a different layer of the same record. The mineralogy speaks to the conditions of aqueous alteration in the parent body, the temperature, pH, and water-to-rock ratio of the ancient environment in which the hydrated silicates formed. The organic chemistry speaks to the abiotic processes that produce complex carbon compounds in space, and, by implication, to the chemical starting conditions available to the early Earth. The isotopic compositions speak to the stellar environment of the early solar system, the mix of material from different stellar sources that the solar nebula inherited before the sun ignited. The pre-solar grains speak directly to stars that no longer exist. Every analysis is a different question addressed to the same material. The material does not change, but each technique illuminates a different part of what it carries, the way a single landscape looks completely different in visible light, infrared, and ultraviolet. One set of findings that emerged in the first year of analysis deserves particular attention: the detection of nucleobases. Nucleobases are the nitrogen-containing ring structures that form the information-carrying components of RNA and DNA. There are 5 nucleobases in the canonical set used by Earth's biochemistry: adenine, guanine, cytosine, thymine, and uracil. Adenine, guanine, and cytosine appear in both DNA and RNA. Thymine appears in DNA, uracil appears in RNA. Uracil had already been detected in the Ryugu sample by the Hayabusa 2 science team, reported in a landmark paper in Nature Communications in 2023. Its presence was attributed to abiotic chemistry, the same photochemical and hydrothermal processes that produce amino acids in carbonaceous asteroids were capable of producing nucleobase structures. The Bennu sample analysis confirmed the presence of nucleobases as well, not just uracil, but evidence for other nitrogen-bearing aromatic compounds in the same chemical family. The significance of this finding requires careful framing. The detection of nucleobases in an asteroid sample does not mean that life existed in the asteroid, or that the asteroid was carrying life, or that the nucleobases were produced by biological processes. Nucleobase structures can be produced by known abiotic chemical pathways, photochemical reactions in ice mixtures, Fischer-Tropsch synthesis in hydrothermal environments, Strecker synthesis in aqueous solution in the presence of ammonia and hydrogen cyanide. What the finding demonstrates is that the chemistry capable of producing nucleobases, the information-carrying molecules of life, operates in the early solar system environment independently of any biological process and is distributed through the asteroid population. The implication for the origin of life is not that life arrived from space. It is that the chemical precursors to life arrived from space or were produced on Earth from delivered starting materials, and that the molecular toolkit from which life assembled itself was available on the early Earth, at least in part because asteroid bombardment delivered it. This is the hypothesis of abiogenesis from exogenous delivery. It is one of several competing hypotheses for the origin of life, alongside hydrothermal vent chemistry, UV-driven chemistry in tidal pools, and others. None of these hypotheses are mutually exclusive. The origin of life was almost certainly not a single event at a single location. It was a process, a long, complex, contingent series of chemical steps occurring in multiple environments over tens or hundreds of millions of years. Different environments, including asteroid-delivered organic material, hydrothermal vents, atmospheric chemistry, and tidal pool chemistry, may all have contributed different components to the eventual emergence of self-replicating molecules. The Bennu sample does not answer the question of how life began, but it narrows the search. It removes from the mystery the question of whether the right chemistry was available. The chemistry was available. It was arriving from space. The sulfur chemistry of the Bennu sample has also attracted scientific interest. Sulfur is an element with complex chemistry in both geological and biological contexts. In geological settings, it exists in multiple oxidation states and forms a variety of minerals, sulfides, sulfates, elemental sulfur. In biological settings, sulfur is a key component of certain amino acids, methionine and cysteine, of coenzymes, and of the biochemistry of certain types of microorganisms, particularly those associated with hydrothermal vent environments. The Bennu sample contains sulfide minerals, iron sulfide phases, in forms consistent with formation under reducing conditions in an aqueous environment. These minerals are chemically related to the iron sulfide compounds found at hydrothermal vents on the modern Earth's ocean floor, where they form through the reaction of sulfur-rich hydrothermal fluids with iron-bearing seawater. Some origin of life researchers have proposed that iron sulfide mineral surfaces at hydrothermal vents could have served as catalysts for the prebiotic chemical reactions that eventually produced life's molecular machinery, a hypothesis associated with the work of chemist Gunther Weierstrass, developed in the 1980s and 1990s. If sulfide minerals delivered by carbonaceous asteroids to the early Earth contributed to the chemical environment of early hydrothermal systems, then asteroid delivery and hydrothermal vent chemistry are not competing hypotheses for the origin of life. They are complementary stages of the same process. The mineral context of the organic compounds in the Bennu sample is also informative. In the Murchison meteorite and in the Rygu sample, organic compounds are not randomly distributed through the mineral matrix. They tend to be associated with specific mineral phases, particularly with phyllosilicates and with carbonate minerals, in ways that suggest the organics formed an intimate association with those minerals, or were adsorbed onto their surfaces during the aqueous alteration phase. Mineral surfaces can catalyze organic reactions, concentrate organic molecules from dilute solution, and protect organic compounds from degradation. The relationship between mineral matrices and organic chemistry in asteroids may be directly relevant to understanding how organic molecules became concentrated and activated on the early Earth, a step that many origin of life researchers consider critical since the prebiotic ocean was too dilute to support the organic reactions required for the emergence of life without some concentrating mechanism. Clay mineral surfaces, like the phyllosilicates found in Bennu, are known to adsorb organic molecules, concentrate them from solution, and in some cases catalyze specific chemical reactions. Laboratory experiments have shown that RNA-like polymers can form spontaneously on clay mineral surfaces in conditions thought to resemble those of the early Earth. If carbonaceous asteroids delivered both the organic molecules and the clay mineral surfaces to the early Earth, they delivered not just the molecular building blocks, but also one possible reaction scaffold on which those building blocks could assemble. The asteroid, in this picture, is not just a courier, it is also a reaction vessel, a mobile chemistry laboratory that spent hundreds of millions of years performing aqueous chemistry in its interior, then delivered the products to the early Earth, along with the mineral surfaces on which the next step of chemistry could occur. Every aliquot sent to research teams around the world is being read with all of this context in mind. Every result from every laboratory is evaluated not just as an isolated finding, but as a data point in a much larger effort to understand the chemical pathway from the collapse of a solar nebula to the emergence of the first self-replicating molecule on the surface of a young planet. That pathway stretches across 4.56 billion years and across the distance between the asteroid belt and Earth's early surface. It is one window into that pathway. Not the only window, but the clearest window that has ever been opened. To understand where Bennu fits in the broader population of near-Earth asteroids, it helps to understand how that population came to exist. The asteroid belt, the region between the orbits of Mars and Jupiter, spanning roughly 2.2 to 3.2 astronomical units from the Sun, contains hundreds of thousands of bodies, ranging in size from Ceres, at nearly 1,000 kilometers in diameter, down to objects too small to be detected by current telescopes. The total mass of the asteroid belt is small by planetary standards, approximately 4% of the Moon's mass, or less than 0.001% of Earth's mass, because the gravitational influence of Jupiter prevented the material in that region from accreting into a planet during solar system formation. Jupiter's gravity did more than simply prevent planet formation in the asteroid belt. It created a dynamic environment of gravitational resonances, specific orbital periods, where the periodic gravitational tugs of Jupiter act constructively, progressively perturbing objects into increasingly eccentric orbits. The Kirkwood gaps, regions in the asteroid belt where the density of asteroids drops dramatically, mark the locations of these resonances. Objects that drift into these regions through slow orbital evolution, driven by the Yarkovsky effect, by collisions, or by other dynamical processes, find their orbits increasingly perturbed until they either fall into the sun, are ejected from the solar system, or cross into the inner solar system as near-Earth objects. This is the mechanism that continuously replenishes the near-Earth asteroid population. Near-Earth objects are not primordial inhabitants of the inner solar system. They are recent arrivals, geologically recent at least, from the main belt, delivered into inner solar system crossing orbits by the combination of slow Yarkovsky drift and resonant gravitational perturbation from Jupiter. The typical dynamical lifetime of a near-Earth asteroid before it is either destroyed in a planetary collision or ejected from the inner solar system is on the order of a few million to a few tens of millions of years. Bennu's current orbit has a dynamical lifetime estimated at roughly 1.75 million years before it will either collide with the Sun, be ejected, or impact a planet. In this context, the 2182 potential impact date is not some distant speculative event at the far end of Bennu's existence. It is near the beginning of Bennu's remaining dynamical lifetime as a near-Earth object. Bennu is, in geological terms, a transient visitor to the inner solar system, a body that drifted in from the outer asteroid belt within the last few million years, is currently threading a complex web of orbital resonances and planetary encounters, and will, within a few million more years, be gone from this region of space one way or another. The 2182 date falls within the window when Bennu is passing through the most gravitationally complex region of its current trajectory, making close approaches to Earth every 6 years, experiencing the accumulated Yarkovsky drift, threading potential keyholes in its 2135 encounter. The question of planetary defense, of whether humanity will need to or be able to alter Bennu's trajectory before 2182, has a timescale that is long relative to a human lifetime, but short relative to the geological context. Decisions about whether to attempt a deflection would need to be made at minimum decades before the potential impact date, to allow sufficient time for any deflection technology to produce the required trajectory change. The earlier a deflection is applied, the smaller the required velocity change, because a small change applied early propagates into a large positional difference by the time of the close encounter. This is the fundamental logic of planetary defense. Time is leverage. If the refined trajectory calculations in the 2040S or 2050S indicate that Bennu's 2135 keyhole passage remains a concern, the window for effective intervention extends from roughly 2050 to 2100. Within that window, a kinetic impactor mission, similar in concept to the DART mission that successfully altered Dimorphos's orbit in 2022, could be designed, launched, and executed. The required delta V for a Bennu deflection, applied sufficiently early, is on the order of centimeters per second, a velocity change so small that it is well within the capability of existing spacecraft propulsion technology. The information needed to design that intervention, Bennu's precise mass, its internal structure, its surface mechanical properties, its Yarkovsky drift rate, is exactly the information that OSIRIS-REx spent 2 years collecting. The mission was, in part, the reconnaissance for a future decision that humanity may need to make. The near-Earth asteroid population that Bennu belongs to numbers in the thousands of known objects and an estimated total population of perhaps 1 million objects larger than 1 meter across. The fraction of this population that has been cataloged and had its orbit precisely determined is still incomplete, particularly for objects smaller than 140 meters in diameter. The ongoing survey programs, Pan-STARRS, the Catalina Sky Survey, ATLAS, are systematically expanding the catalog. The upcoming Vera Rubin Observatory, whose legacy survey of space and time will begin full operations in the mid-2020s, is expected to discover hundreds of thousands of additional solar system objects, including many near-Earth asteroids currently unknown. Each newly discovered object is a new data point in the map of what is out there. Most will turn out to be non-threatening, their orbits carefully calculated, their impact probabilities confirmed to be negligibly small, their trajectories monitored but not actively concerning. Some small fraction will require closer attention. Bennu is currently at the top of the list of objects requiring attention, not because its impact probability is large in absolute terms, but because it is the largest, most precisely characterized, and most well understood potentially hazardous object for which a non-negligible impact probability has been calculated on a specific future date. It is the test case for whether humanity has developed, in time, the scientific and technical capability to understand and, if necessary, alter the trajectory of a natural object moving through the solar system. The answer, as of the mid-2020s, is probably. The knowledge exists, the technology exists. The question is whether the institutions, the political will, and the lead time are in place to act when or if they are needed. That is a question OSIRIS-REx cannot answer. It did its part. What remains unknown about Bennu is itself scientifically informative. Despite 2 years in orbit, contact with the surface, and the return of 121 grams of material, there are aspects of Bennu that are genuinely unresolved. The interior structure of Bennu has never been directly sampled. The tag contact reached 48 centimeters below the surface at Nightingale, but this is a tiny fraction of the approximately 245-meter radius of the body. What lies beneath the outer layer, whether the rubble pile structure is uniform throughout, whether there are coherent rock masses embedded in the aggregate, whether the porosity varies with depth, is not known. Several lines of indirect evidence address this question. The radar-derived bulk density and the estimated surface material density together constrain the average porosity, the rotational behavior of the body, its spin state, the equatorial bulge, the absence of obvious shape asymmetries, provides additional constraints on the internal mass distribution. The particle ejection events, with their implications for volatile compounds near the surface, suggest at least some compositional stratification. But the interior of Bennu is uncharted territory. Future missions, if funded, could probe it directly. Seismic instruments deployed on the surface, similar in concept to the Apollo lunar seismometers or the InSight lander's seismometer on Mars, could detect the propagation of elastic waves through the interior and reveal its structure from the patterns of wave reflection and refraction. Radar sounding, similar in principle to the CONSORT instrument on the Rosetta mission that attempted to probe Comet 67P's interior, could image subsurface structure at meter to tens of meter scales. Neither of these instruments flew on OSIRIS-REx. The mission's payload was constrained by mass, power, and cost within the New Frontiers budget. The science instruments selected maximized the value of the sample return and the surface characterization. The interior was a trade that was made. The particle ejection mechanism is also unresolved. Despite the detailed analysis of 19 documented ejection events, the relative contributions of thermal fracturing, meteorite impacts, and volatile sublimation to the observed phenomenon remain uncertain. No single mechanism conclusively explains all of the observed events. This matters not just for understanding Bennu specifically, but for understanding the broader physics of active small bodies. The class of objects that includes active asteroids, main belt comets, and the active centaurs in the outer solar system, all of which display some level of surface activity driven by processes that are not fully understood. And the sample itself will continue to pose questions. As analytical techniques improve and new aliquots are studied by new research groups with new instruments, findings will emerge that raise interpretive challenges, results that don't fit neatly into the existing framework, mineral assemblages that imply conditions not previously modeled, organic compounds with structures that don't match known abiotic synthesis pathways. This is how science works. The sample does not provide answers that close questions. It provides answers that open new questions, more specific, more precisely constrained, harder to answer than the questions that motivated the mission in the first place. That contact at Nightingale Crater in October 2020 was not an ending. It was a beginning of a different kind. The beginning of a conversation between a piece of the early solar system and the instruments of a civilization that formed from that same solar system, asking the material to explain itself. The material has been answering, slowly since September 2023. It will continue answering for decades. Right now, Bennu is out there. Not in a photograph, not in a simulation, in space, physical space, the same space that contains this planet, this solar system, this moment. It is 490 meters across. It is rotating, completing one full turn every 4.3 hours, its equatorial ridge catching and releasing sunlight in a slow rhythm that is continued for longer than the Earth has existed. Its surface temperature rises and falls with each rotation, from the hard cold of the night side to the heated exposure of the noon surface, cycling through 200 degrees of temperature range in the span of a little over 4 hours. The Nightingale Crater is there. The disturbance left by OSIRIS-REx's 5-second contact is still visible in the regolith, a roughly 8-meter depression where material billowed outward and settled again under Bennu's microscopic gravity. That is the most recent mark on Bennu's surface, left by anything other than natural forces. In 10,000 years, micrometeorite gardening and thermal cycling will smooth it back into the surrounding terrain. The mark left by a spacecraft from another planet will be erased, as everything on Bennu's surface eventually is. But the chemistry the contact revealed will still be there. That does not erase. The near-Earth asteroid population Bennu belongs to is not a stable fixture of the inner solar system. It is a transient population, continuously replenished from the main asteroid belt and continuously depleted by impacts, gravitational ejections from close planetary encounters, and the rare event of tidal disruption as a body passes close enough to a planet that differential gravitational forces overcome the body's internal cohesion. The current estimated population of near-Earth asteroids, larger than 1 kilometer, the size threshold above which a surface impact would generate sufficient ejecta and thermal pulse to produce regional climate effects, is around 900 to 1,000 objects. NASA's Planetary Defense Coordination Office estimates that roughly 95% of these kilometer-plus objects have now been discovered, cataloged, and had their orbits determined with sufficient precision to confirm they pose no impact risk within the next century. The situation for smaller objects is less complete. For bodies in the 140-meter range, large enough to cause regional devastation comparable to a major nuclear weapon, the estimated catalog completeness is roughly 40% of the actual population. For objects in Bennu's size range, 400 to 500 meters, completeness is estimated at 60 to 70%. The remaining uncatalogued fraction is the principal motivation for expanded survey capability. Survey programs currently operating include PAN-STARRS, the Panoramic Survey Telescope and Rapid Response System, operating from Haleakala Observatory in Maui, the Catalina Sky Survey, operating from the Catalina Mountains north of Tucson, and ATLAS, the Asteroid Terrestrial Impact Last Alert System, a network of small telescopes at multiple sites that specifically targets the days to weeks warning window for incoming objects. These programs discover dozens of near-Earth asteroids every week. The Vera Rubin Observatory in Chile, whose legacy survey of space and time will conduct the deepest and most comprehensive survey of the night sky ever attempted, is expected to increase the known near-Earth object catalog dramatically when it reaches full operations. Its 8.4-meter primary mirror and 2 billion pixel camera will detect objects many times fainter than current surveys, revealing the population of smaller near-Earth objects in detail previously inaccessible. Every newly discovered object is a new data point. Every new data point is an opportunity to confirm a non-threatening trajectory, or, occasionally, to identify something that requires closer attention. The night sky is still being searched. Every clear night, automated telescopes sweep their assigned fields, comparing exposures taken hours apart, looking for the motion signature of something new. Most of what they find is known. Some of it is not yet. The radar facilities available for asteroid orbital characterization have changed since OSIRIS-REx was at Bennu. The Arecibo Observatory's 305-meter dish, the world's most sensitive single-aperture radio telescope for most of its operational history, which provided critical radar astrometry of Bennu that enabled the first Yarkovsky measurement in 2013, collapsed catastrophically in December 2020. The failure was caused by deterioration of the cable suspension system that supported the 900-ton instrument platform above the dish. The loss of Arecibo removed the most powerful asteroid radar capability that existed. Goldstone's 70-meter antenna at the Mojave Desert facility continues to provide planetary radar observations, though with less sensitivity than Arecibo offered at its operational peak. Plans for a next-generation Arecibo replacement, a multi-antenna array in Puerto Rico have been proposed and are in various stages of planning and funding consideration. The absence of Arecibo's capability creates a gap in the planetary defense observation infrastructure at exactly the time when the asteroid threat is best understood and the need for precise trajectory data is most clearly articulated. Bennu's trajectory will be monitored through whatever radar and optical capabilities are available, through each successive close approach. Each additional data point from each close approach, whether from radar ranging, optical astrometry, or eventually additional spacecraft reconnaissance, will refine the probability estimate for 2182 further. The current estimate of 1 in 2,700 is itself an improvement over the estimate available before OSIRIS-REx. The mission's 2 years of spacecraft tracking, producing precise measurements of Bennu's position and velocity from close range, and providing a direct measurement of the Yarkovsky drift, reduced the uncertainty in the 2135 keyhole passage geometry by a factor of 8 compared to pre-mission models. That factor of 8 improvement in trajectory uncertainty did not by itself reduce the impact probability to 0. It moved the probability from an uncertain range to a more precisely constrained value. The 1 in 2,700 figure is a better estimate than anything available before the mission, more honest, more grounded in precise data, less contaminated by uncertainty. Whether the true probability, the actual physical outcome that will eventually occur on September 24th, 2182, is 0 or non-zero, is something no current calculation can determine. The calculation will converge as time passes and as additional data accumulates. In approximately 30 years, when Bennu makes a close Earth approach in 2054 and the new observations are folded into the trajectory model, the probability estimate will change again. By the 2080s, the picture may be clear enough to make a definitive decision about intervention. The asteroid will not wait. The calculation continues. The asteroid belt itself is a record of what the inner solar system did not become. Jupiter's formation, which current models suggest occurred rapidly within the first few million years of solar system history, established a gravitational boundary that prevented the material between approximately 2.2 and 3.2 astronomical units from accreting into a planet. The mass that accumulated in that region was instead subjected to ongoing gravitational perturbation, both from Jupiter and from the resonant effects of its interaction with Saturn. Over the history of the solar system, this gravitational environment has gradually depleted the asteroid belt of most of its original mass, through collisions, through ejections into the inner and outer solar system, and through the slow Yarkovsky drift that carries objects into resonant zones, and from there into planet-crossing orbits. The current asteroid belt mass, approximately 4% of the Moon's mass, is estimated to be a small fraction of the material originally present in that region. The depletion was particularly severe during the period of giant planet migration, the epoch in solar system history when Jupiter and Saturn may have migrated significantly from their formation positions, sweeping through resonances that destabilized the orbits of enormous quantities of material. That migration, on the widely accepted planetary evolution models, triggered the late heavy bombardment, delivering a flux of carbonaceous material from the outer asteroid belt into the inner solar system around 3.9 billion years ago. Bennu, or more precisely the parent body Bennu came from, was part of that outer reservoir. Its material, the hydrated silicates, the organic compounds, the precellar grains, formed in the outer reaches of the asteroid belt, where temperatures were low enough for volatile compounds to condense and for liquid water to exist transiently inside larger bodies. The carbon-rich composition, the water-bearing mineralogy, the amino acid chemistry, all of these are signatures of formation in the cooler, more volatile-rich outer belt at distances from the sun, where conditions favored the preservation of the most primitive solar system chemistry. That material has been orbiting the sun for 4.56 billion years in various configurations, first as part of a larger parent body, then as part of the shattered fragments of that body, then slowly reaccumulated into the loose aggregate that is now Bennu, then gradually perturbed by the Yarkovsky effect into a resonance zone, then delivered into the inner solar system in the last few million years. The chemistry that may have helped start life on Earth spent most of its history in the cold outer asteroid belt. It has only been in the inner solar system, close enough to Earth to interact with it, for a geological eye blink, and in that eye blink, humanity managed to go find it. The asteroid does not know any of this. It simply orbits. The equatorial ridge catches the sun on the afternoon side, slightly warmer than the morning side, radiating heat into space and slowly, imperceptibly, pushing the orbit a few hundred meters outward each year. The boulders on the surface cast shadows that move across the crater floors as Bennu rotates, the shadows lengthening toward local sunset, the surface temperature beginning its long, slow drop toward the cold of the night side. The Nightingale crater floor, undisturbed except for that brief contact in October 2020, holds its material in the configuration it has held for millennia. The hydrated silicates, the phyllosilicates bearing the crystallographic signature of the ancient water that formed them, absorb and re-emit sunlight in wavelengths that, if a spectrometer were present, would identify them unambiguously as the products of aqueous alteration. The organic compounds remain where they have always been, adsorbed to mineral surfaces, embedded in the fine-grained matrix, waiting. The presolar grains, the stellar dust from stars that no longer exist, retain their anomalous isotopic ratios in the cores of their mineral structures, unchanged since they condensed in the atmospheres of their parent stars billions of years before the sun formed. All of it is there, rotating, cooling, warming, cooling again. The solar system is very patient. It has been here for 4.56 billion years. It does not require anything of Bennu except that it obey the physics. And so it does. There is a specific quality to the silence in the space around Bennu that is worth understanding precisely. Space is not empty in the physical sense. It is permeated by solar wind protons and electrons streaming outward at hundreds of kilometers per second, by photons from the sun, by the faint flux of cosmic rays from distant supernovae, by interplanetary dust in slow orbital motion. But there is no medium for sound, no atmosphere to carry mechanical vibration from the cracking of a thermally stressed rock to a receiver anywhere else on the surface, no wind, no pressure. The surface temperature swings 200 degrees in 4 hours, stressing the rocks in silence. When a boulder fractures under the thermal load, when the crack propagates through the crystal structure, and the fragment lifts slowly away from the surface and drifts into a low orbit above Bennu before falling back. There is no sound. There has never been any sound. Not in the years since Bennu formed from the reaccumulation of its parent body's fragments. Not in the millions of years of its current inner solar system orbit. Not during OSIRIS-REx's contact. The most significant event in Bennu's recent history, the arrival, the study, the touch, the departure of a spacecraft from another planet, happened in complete silence. The solar system is a silent place. Everything that has ever happened in it, every collision, every eruption, every impact, every gravitational capture, happened in silence. The only sound in the history of the solar system that we know of has happened on the thin atmospheric layer of one small planet. Everything else has been silent. Bennu will continue in silence. If it passes through the keyhole in 2135 and strikes Earth in 2182, that too will not be silent. The hypersonic passage through the atmosphere, the impact itself, the shock wave, but the approach will be. The long arc from the asteroid belt to Earth's atmosphere will happen in the same silence in which everything else happens. The rock does not know what it carries. It does not know about the amino acids, or the presolar grains, or the keyhole calculations, or the laboratory in Houston. It rotates. The mathematics takes care of the rest. If you have traveled this far tonight, through the discovery, through the orbital mechanics, through the spacecraft, through the contact, through the chemistry, through the silence, then you have seen the story from beginning to present. There is a thread that runs through the history of science that is worth tracing to its present end. In 1801, Giuseppe Piazzi at the Palermo Observatory in Sicily detected an object that moved against the fixed stars. He could not follow it long enough to determine its orbit before illness forced him away from the telescope. Carl Friedrich Gauss, then 23 years old, used the brief arc of observations Piazzi had managed to collect and applied a new mathematical method he had developed to predict where the object would be found again. The object, named Ceres, was recovered from Gauss's prediction. It was the first asteroid ever discovered. It is now classified as a dwarf planet, the largest body in the asteroid belt, 940 kilometers in diameter. The mathematical methods Gauss developed to recover Ceres, the method of least squares, which is still fundamental to statistical estimation, were developed because of an asteroid. The practical need to predict where a moving body in space would be drove the development of a mathematical tool that has been applied to virtually every quantitative scientific discipline in the 2 centuries since. The Murchison meteorite raised this question in 1969. 5 decades of analysis could not fully answer it because every meteorite arrives contaminated by Earth. The Bennu sample, returned under controlled conditions in 2023, is the first contribution to that conversation not burdened by that limitation. The DART mission in September 2022 demonstrated that a kinetic impactor could change the orbit of an asteroid. The test was designed and executed against a non-threatening target, Dimorphos, the moonlet of Didymos, specifically because testing planetary defense technology requires a target, and testing it against a threatening asteroid would defeat the purpose. The result, a 33-minute change in Dimorphos's orbital period, substantially exceeding the predicted 73-second minimum, confirmed that the kinetic impactor approach works, and that it works better than the conservative predictions because of ejecta enhancement. The European Space Agency's Hera mission, launched in October 2024, is traveling to Didymos to study the aftermath of the DART impact in detail, measuring the crater it produced, characterizing the changes to Dimorphos' surface, and precisely determining the mass and interior structure of both bodies to build a complete model of the deflection. The combined DART and Hera dataset will produce the most precise characterization of a kinetic deflection event in history, turning a demonstration into a calibrated scientific measurement. The information from OSIRIS-REx about Bennu's rubble pile structure and surface mechanical properties will be combined with the DART Hera dataset on Dimorphos, another small rubble pile, to build increasingly accurate models of how kinetic deflection works on bodies of this type. The planetary defense science of the 2020s and 2030s is in retrospect laying the technical and scientific foundation for whatever decision humanity may eventually need to make about Bennu specifically. That decision point, if it comes, is likely in the 2060s to 2080s, far enough from 2182 that a deflection mission would have time to work, close enough to the 2135 keyhole passage that the trajectory uncertainty will have been substantially reduced. The people who will make that decision have not yet been born. The science being done today, the trajectory refinements, the sample analysis, the kinetic impactor calibration, is being done for them. Science is rarely done for the moment in which it occurs. It is done for the moments that follow, the moments when the knowledge will be needed, when the instruments of the present will be inadequate, and the data of the past will be the only thing available. OSIRIS-REx did its science for the people of 2060 and 2080 who will need to make decisions with stakes that exceed anything the mission team in 2023 could fully comprehend. The solar system does not adjust its schedule to human concerns. The asteroid belt does not pause while the funding decisions are made. The missions are proposed and rejected and finally approved. The spacecraft are built and launched and operated, and the samples are analyzed. Bennu's orbit proceeds on its own timeline. The mathematics of the solar system is indifferent to the capacity of the civilization within it to understand or respond. What that civilization has managed in the decades since Linear's automated software flagged a moving object in September 1999 is to go from discovery to orbital characterization to spectral analysis to mission design to spacecraft construction to launch to a 2-year orbital survey to a brief surface contact to sample return to laboratory analysis in 25 years. From a point of light in a telescope image to 121 grams of dark dust in a clean room, studied by hundreds of researchers on multiple continents, its chemistry being compared to the chemistry of the early Earth. That is what 25 years of focused scientific effort can accomplish, when the question being asked is important enough and the commitment to answering it is genuine. The trajectory is being tracked. The material in Houston is being studied. And somewhere in the inner solar system, a rock 500 meters across is doing what it has always done, turning slowly in the dark, carrying 4.5 billion years of chemistry in its dust, following a path that physics calculated for it before any mind existed to observe it. Let that settle. The night is long. The rock is still turning. In, out. Everything you heard tonight is real. Bennu is out there right now. If this kind of science is what you want to fall asleep to, subscribing to Quiet Science at Bedtime means more stories like this one keep coming. Like the video if Bennu will stay with you. Leave a comment, even just one word. Good night.